Alrighty, so we have our Simulink induction machine model, and this video relates to the Simulink induction machine write-up, which I have on my website. I won't go through it, but effectively the video is there to get from the defining equations, which are derived at some length, into how you actually put it all together in Simulink. So I've got the model here. There is a model in Simulink of an induction machine, and you can use that, no problem. It may be the case that you want to derive it so you know how it works, or it may be the case that your professor has told you that you will derive it, and that's that, because they want you to know certain things about it, or they want to be certain that you understand it. It may be the case that you want to extend it somehow in a way that the built-in model isn't easily amenable to. Or it might just be to demonstrate a certain setup that you want to have of your own, rather than having to rely on certain Simulink packages or model toolboxes. So we can start at the left hand side, and we've got some connections for the phases, and we have each phase, we could call them, go away, wretched creature. It says don't show this message again, but I'm pretty sure there are other videos of me where it pops up and says don't show it again, and I click it and it duly puts it into the next video. So we have there is no neutral point here, we've got open windings. It's the business of the person who is modelling the machine with the power electronics and whatever else is used to decide how that machine's wired up. They need to be able to wire it in star or delta, with or without a fourth wire, a neutral wire. So we will just give them call it plus or minus, but you could say dot and non-dot if you prefer, because secretly we know their inductance is with a series resistance. So if you're reading the text, you'll know that my preference is to model the entire system as a controlled current source, in order that we don't end up with a singular matrix in our simulation due to the connection of voltage sources. And this is certainly true if you're using a voltage source inverter. If we ended up impressing a voltage across these terminals, and this was a voltage proportional to effectively the back EMF, we'd end up, and there were no resistances as well, we'd end up in a situation where two voltage sources have been connected together, and Simulink will either insert a little resistance for us, which is not really desirable because we need to be in control of what Simulunk's getting up to, or it will throw us an error, which is more desirable than the inserting a little resistor, but it's still not very desirable because it is traditional for simulations to run properly. So we have our measurement of the voltage across the phase, and we have a current which is drawn by the machine from the phase, proportional to some calculations that we will do, which are off the right hand side of the screen. And three-phase machines, so we've got three phases. If it's dual three-phase, or you want some weird five-phase machine, or whatever you choose, you can, this is a copy-paste job. So we're taking in the voltage measurements, and we're sending back some currents that we want to draw out of the windings in accordance with the calculations we're going to do. So if we zoom out a little bit, we've got a set of machine parameters that we're going to put in, and these will be the machine parameters which are given in the documentation. So we've got the synchronous speed in radians per second, and we've got the mutual inductance, we've got the rotor leakage inductance, we've got the stator leakage inductance, number of pole pairs, and the mechanical inertia of the rotor and whatever the rotor is connected to. Other things we have are the load torque and the frictional torque. So this is if you were connecting this machine to, say, a gearbox, for example, and you know that there's connected to the other end of the gearbox there's some other things you need to drive, like a fan load or something like that, you might try to model the torque which is produced by the aerodynamic effects of the fan load. It might be proportional to the speed squared or the speed cubed, or whatever you want to say, and you have some load torque value that is derived from that, and you know the speed because you have the rotor speed. What is more, there will be some bearings in this gearbox for example, and they will have some frictional drag, and of course there will be friction for the fan and everything else, so maybe we have some frictional torque as well. And in the model, in the write-up, that's called D. I don't know if it's called D in the diagram. I haven't labelled it. Very naughty. I could label it D if I wanted to. The way you do the labelling is you just double click the wire. That would be how you did it. I could call that TL as well. I did it somewhere else. Good. That's alright then. So there's a fair bit of sorry, I should zoom out up here, up down there. That's it. It's so far away. So we have these are our voltages which are impressed on the machine windings, and we've got our ABC to DQ. So this deals with the Clark Park for us. It's a built-in Simulink block. I can't really look inside it because Simulink doesn't allow that sort of thing. But I've set up this is the standard. You can choose another as well. It really doesn't matter too much which you choose. I will leave it as this one. All it means is there'll be phase shifts in your answers. So we've got our DQ, and we are going to apply this to the calculation of the fluxes. So we calculate the fluxes first, then we do our calculation of the currents from the fluxes, then we do our calculation of the torque, electromechanical torque, then we do our calculations of the mechanical system. This gives us the torque on the shaft, the speed of the shaft, so on and so forth, and these parameters are fed back from variously from there, and there. Having DQ to ABC them goes back to give us our currents that we are drawing out of the supply. In fact, it's this block here, which tells us that we've got our, so this is the stator referred DQ currents are DQ to ABC, and the DQ to ABC with the omega of the rotor, and then they are injected back into the, is it the rotor? Pardon me, it might not be. Let's have a quick look. Omega S, the stator is this, omega T is the stator here, which makes a lot more sense. So we have the stator currents in ABC reference frame, and they are what's fed back to the, effectively the windings that we are connecting up as if they are the stator. So there we do a little bit of calculation here, which I'll come back to in a bit. So if I was to go into the stator flux block, I've got the synchronous speed, I've got the stator voltage in DQ, and I've got the stator current in DQ, which is fed back from this calculation. So not only are the fluxes calculated with respect to each other, so for example if I look at this wire here, sorry, not that wire there, one of these wires, there are elements inside this block. Oh, here we go, yes. So the stator flux is calculated based on the stator DQ current because of this feedback here, and the rotor flux is calculated partly based on the rotor current. But to calculate the rotor current we must first solve for the flux, because of this 4 wire here in the case of the rotor, and this wire here in the case of the stator. So Simulink has to solve all of these equations simultaneously. So if we go into the stator flux, hopefully try to get it where the camera cannot block any of it. There we go, that's about right. When I say the camera, I mean the picture of me, which is down here. So we have our synchronous speed in rads per second. Probably should have put some units on there, but never mind. The stator voltage in DQ and the stator current in DQ. And we have, now I've cheated a bit here and I've put some constant blocks in. In ideal situation, if you've got a much larger simulation where this motor is a part, or generator is a part of something else, it would be preferable to, instead of hard coding this stuff, load it up from the workspace when you start the simulation. So you would have all your parameters in the MATLAB script, you'd call the script, then you'd fire up Simulink and open your simulation model, and your simulation model will call from the workspace the things that you've loaded with the script. And of course the script is just a list of constants. And if you want to run several different scenarios, maybe you have I don't know, suppose you're in automotive and you're doing some hybrid stop-start, and you're fervently waiting for the day that 48 volt comes along, because we've all been waiting for quite a long time. Still isn't really here. Might even be 42 volts, depends who has their way. You might think, oh, we will simulate with the 12 volt machine and then we'll simulate with the 48 volt machine, and maybe we want to do not just a stop start, but we also want to do a boosting or a power assist, which is a slightly different machine, and we will run at slightly different speed, maybe put it into a different point in the transmission system. So we have to have different models for each of them. Overall induction machine model, of course, is the same. As long as it's an induction machine that you intend to use, then there's no reason why you couldn't load up different scripts and run the same set of model files. The way I've done it here, it's hardwired, which is not as elegant and it's not as useful, but this is just an example. So I've got my stator resistance measured ohms, and I'm doing some multiplications. What I'm doing here is I'm developing the d flux by dt for the stator. So if we went back to the document and I scroll up to the appropriate spot, this is the d flux by dt follows this expression here. Is that the one I'm after? Yes, it is. Effectively, it's these set here. For the rotor and the stator. These are just the stator, of course. The rotor's in a separate sub-diagram. So this is the stator d-axis, this is the stator q-axis, and this is the expression I'm developing. VSQ minus ISQRS plus, I call it phi. I know it's lambda in this document, but I wrote it in my lab book as lambda, and I'll have to change it to phi later. So when you download this, it'll probably have phi there, but there we go. Phi SQ omega S, and you'll integrate that, and of course you have to take something back from here and feed it back, which is the Phi SQ omega S, because it's multiplying it. Oh, it's added to, so subtracted from the VSD ISDRS, and that yields this bit. Then we integrate, and that gives us the Phi SD. So this lot is the text form of one of these. It's a very good idea to label up your wires like this. So that's how we derive the flux, or not derive, produce the Phi SDQ. Going back in, I've got the rotor flux as well, exactly the same setup. I've hardwired the rotor resistance when I could, of course, have taken it off the workspace. And I have the same arrangement, slightly different equations, same method. We develop the differential equation, then we integrate. Nothing unusual there. Then we want to get from flux to current, so we have the four flux equations. They're derived from these four, 7 through 10, but I write them out, or I write two of them out further down in the form that I actually implement them. I didn't bother to write out the other two because it's not difficult to see from 11 and 12 that you'll end up with a IQR and an IDR that have some fluxes and some currents and inductances on the top, and they'll have some LM plus LLR on the bottom, or denominator. Obviously this is not the website of the video, because the video doesn't exist yet. I'm recording it now. So we will have a look at the current block. So inside here I've got 4 blocks, each for one of the currents. I take in the two sets of fluxes, and I've got some parameters that I took from way back. So if I go back here, I've got some one of the things I've never liked about Simulink is the way it likes to zoom in on things. This is where I started the video. I've got some machine parameters here, and I'm feeding those up into the fluxes to currents. subdiagram and they appear here. You could draw these from the workspace as well, in which case you don't need to pass them around in wires, and that would be a very sensible thing to do. So if I just look at one, and this is the, well, we'll do one that's actually in the sheet, the stator Q axis. There really isn't very much to it. I didn't even bother to label it, which is perhaps a little naughty. But all this does is implement, which was it, Q or D? Q. It implements that expression there, flux minus Lm IRQ all over Lm plus LLS. This is Lm plus LLS added, and then dividing this bit here. Reasonably trivial stuff. So there's 4 lots of that, and they produce the IR and the IDQ. And you will note that there is feedback from IRDQ to calculate ISD and ISQ, and there is feedback from ISDQ to do the calculation of IR and ID. So once again, Simulink has to solve this lot simultaneously. So once we've got some currents, we can do some torque calculations. So this is the equation a little bit longer here, so I've decided that it's in my best interest to write them out properly. If you don't write out the equations, what you'll probably find is it doesn't work. And then you have to sit down and figure out why. It's the same with how neatly you draw out the diagrams. If you don't draw them out neatly, it just makes it a rat's nest, and then you have a hell of a time figuring out what's going on. So we've got our ISD, our IRD, our ISQ and IRQ, and they're just unmultiplexed. And we are effectively working our way towards 3/2 times the number of pole pairs times some currents times some inductances. Actually, these are just fluxes, but if you go back here, I didn't like the idea that I have to put fluxes straight in here from here and go round the side. Since I have the current here and the general flow of the diagram is left to right, I would prefer to take the currents in and do a little bit more calculating. You can of course see things differently and put this block down here maybe and couple that straight to this. That would be alright as well. Anything that works is fine as long as you can explain it. So I wouldn't bother to, I mean, this equation is this equation here, it's 13. It's just written out uglier. We're just adding up and multiplying and doing the things we need to do. Or it's a slight mistake here. If you look, there's no 3/2 in this wire. The 3/2 is actually on this wire because here's my 3/2 gain block. But never mind. It's just a minor thing. And we get out the torque. Then we will do some calculations of the mechanical system. So we take the electromagnetic torque in, we take in the frictional torque which is supplied, is the D, we take in the load torque which is supplied, is the T sub L, number of pole pairs, and the inertia which is J, and out of it we're producing, well, the frictional torque is only the frictional torque we took in, but I like to have it as an output because sometimes I want to look at how much friction I've got on in the mechanical system. Essentially it's a way of working out how much useful work I'm getting out of the machine or out of the system the machine is connected to. We also have the rotor speed. I like that in RPM because I like to think in RPM. I don't like to think in radians too much. If I'm dealing with machine, then we think about mechanical degrees and electrical degrees, and I might have to think about radians a bit, but I would prefer to compute everything into RPM. Then I've got my electrical position effectively, which is 0 to 2 pi, and that will loop back. So you'll get a staircase waveform as the machine rotates continuously. I get my electrical speed, which is in rads because that's the common method, and I'll end up with the net torque. And if of course the net torque is positive, the speed of the system will be going up. So we can have a look at the equations in here. And we are effectively doing this differential equation, and then we're probably going to do some integration afterwards. Yes, we are going to do some integration here. And that takes us from the rotor electrical angular velocity to the electrical rotor position. And then we can divide through by 2 pi and do whatever else we need to do. This gain block just has the 60 over 2 pi in it, which gives us rads per second into RPM. So we subtract the load torque from the M torque to give us the net torque before any frictions. Then we take away the friction, and of course the friction coefficient is multiplied by the number of pole pairs dividing the electrical speed. So this is effectively the mechanical speed, and of course the faster the shaft is turning, the more the friction or drag will be, because the bearings are going faster and so forth. Windage as well we can count in there. All of that subtracted from the EM torque effectively. Then we are dividing through by the J. If you go back to the equation, the J is on the bottom. What we've really done is this bit so far. And then we integrate. And we integrate so that we end up with omega Re instead of the d omega R by dt. Then we want to get it into a situation where we have some outputs that we like the look of, and the rest of it is really just making it nice. If you've got other parameters you want to take out at this point, do some trivial calculations here to get, I don't know, maybe you want a theta mechanical, for example. You could do that, no problem. With the theta electrical, we must take it out and use it to do some calculations of the rotor currents in the DQ frame back to the ABC frame. We don't actually need to look at these. There's nothing that says, oh, we must inspect them. We don't take them back anywhere into the model, but it's nice to have them. We can see the currents in the rotor bars or rotor windings if it's a wound machine, as the simulation proceeds, and we don't usually have access to that information when we're actually testing the machine on a dyno, unless we've bothered to insert some shunt resistor into the machine, and we can have some, I don't know, some some slip ring on the back, where we can take off parameters for the rotor and measure them using an oscilloscope or whatever. I don't know of anybody that does that. They do their calculations, they do their FE, they run their simulations. If they get the torque and the power they expect and the efficiency that they're expecting, they take it as read that their calculations of the rotor currents will be right. You'd have to be very, very paranoid to make the extra effort of doing a special machine that allowed you to take off the rotor parameters. Sometimes for temperature it's done, but it's much easier in machines where there are slip rings anyway, like a wound rotor machine. A wound rotor synchronous machine. You have to put current into the rotor anyway, so you're going to have a slip ring. So there's no reason why you couldn't put a thermal sensor in there and have a couple of extra slip rings that just take the sense currents out. But in the case of the induction machine, we desperately want to avoid the slip ring. So we don't want to, even if we decided to do some special machine, we'd probably try to avoid that. It adds expense, effectively. So then we say, well, what about this stuff here? This business here is to try to tell the simulation what the omega t is for the DQ transformation. We need to effectively make a fake resolver so that we can do our transformations properly. If you're doing this sort of field orientated control, you will almost always have a resolver. There's no real chance not to. I'd be very surprised if you did, because we need to be able to supply the calculations with the where is the d-axis, because it's always going round inside the machine. We need to know where. So we have our synchronous speed, and we will multiply by 2 pi, and this will give us the electrical synchronous speed, and multiply by the pole pairs, so we know how regularly these 2 pi radians are occurring as we actually traverse through 2 pi mechanical. Take out the 60 because we are usually running in RPM. This will be RPM, I think. Be surprised if not. and then we can integrate to give us position. So all of this business was done in speed, and the position will be the integral of the speed. And then we need to know whereabouts in the particular cycle, because we only want the position between 0 and 2 pi. So we divide through by 2 pi and take the remainder. In other words, we're taking the modulo effectively, and that will give us a position to put into our DQ transformation. It's not necessarily a real position. If you did some work on the bench or in the dyno and then you went back to your simulation, you wouldn't be able to marry up after so many seconds of simulation and so many seconds of actual running. These things will be the same. They won't. It's just to allow us to proceed the simulation. And if you were doing this for real, this will be done inside your DSP or DSpace or whatever it is you're using to run your machine. So that's the overall mechanism. We have some voltages applied to the windings. We have some currents which flow in the windings, or in the quote unquote windings, which are caused by the operation of the machine, which is dealt with by the equations. We have something to work out what the position of the rotor is in DQ frame. We do our transformation, we do our calculations of the fluxes, we use those to do the calculations of the currents, we use the currents to do the calculations of the EM torque, and also the currents are fed back to do the fluxes. Having calculated the torque, we deal with our mechanical system, and you can make a mechanical system as complicated as you like. Then we DQ back to get the rotor currents in ABC frame, just because we can look at them. We also have to go from DQ to ABC to give us the stator currents, which we need to inject back to draw from the voltage sources that are driving the machine. If we were using a current source to drive the machine, we would probably be sending back a voltage, and we would cast these equations, well, not the mechanical system, that would be same. We would cast these equations slightly differently, but it's not beyond the wit of people to derive them if they need to. So if we go up one level to a place before the simulation, the video starts, I've got a giant block, which is the machine, and I've got some AC voltages, and I've got some series resistances, probably not very big. This is not the machine resistance, this is the resistance of the supply. Even if you have a very large capacitor bank full of very low ESR capacitors and very short wires, there will still be some resistance. You may as well put it in. You're probably going to end up modelling it at some point. Machine parameters I have in a block like this. As I say, you can derive them from the workspace. It's probably better to do that. Excuse me. No low torque at the moment, so it should spin up pretty quickly. And frictional tie, I don't know why that isn't inside there. I could put it in quite easily. I'll be looking at the DQ axis stator flux, the DQ axis rotor flux, DQ axis stator currents, rotor currents, ABC frame, stator currents, ABC frame, rotor currents, rotor speed and RPM, the electrical position of the rotor, rad, 0 to 2 pi, then it goes back to 0, electromechanical torque, the low torque, which is the low torque is this one. I'm just passing it through so I can look at it on the same graph without having to wire around the block. Same goes for the frictional torque. The net torque will be the difference of those. And if I go in, that's what that is. So we can run it, I should have thought. These are set up 340 peak. This is 415 phase to phase machine, and I've hooked it in, I guess I've hooked it in star, although I haven't explicitly connected all this point and that point and that point. It is, as far as the simulation is concerned, when we look at the waveforms, you'll see that it's in star. 50 Hertz because we're in the UK, and no phase shift, I should have thought. Yep, no phase shift. Second phase, 120 lagging. Third phase, 120 leading. You could do leading and then more leading, or you can start lagging and have less lagging and then 0. It's entirely up to you. It's all relative. So I can run for say 5 seconds. Hopefully it will simulate quite quickly. We've got the power GUI block down and it's continuous, and there's nothing special about the solver at all. Totally standard settings. We'll have a look at the settings in a minute. And it should start up. The video is in the way, isn't it? And you can't see the time progressing. Let me see if I can move the video. Popping up there for a bit. That was weird. I'm on, I don't know, 3rd or 4th generation i7 laptop at the moment, so it's not a special machine, it's not HPC or anything. So we can have a look at some data. I'm just going to move the video back. Don't like heights, don't want to be in the top corner, it's a bit weird. There we go. Right, so we can have a look at maybe some mechanical properties. Yeah, all that about it being quite a good computer. Yes. Come on, make this a little bit smaller. There we go. I can't remember exactly where the video comes to, but I guess it's probably about there. How does that look? Yeah, believable. I could probably go even a bit further. That'll do. So we have initially, this is the rotor spinning up. Don't forget, there's no saturation in this model, so we can get torque that probably you can't actually get in a machine, because the sort of currents we'll be generating here in the windings will be so large that the machine iron will saturate and you won't get the linear operation that this model suggests. And you can add the saturation if you want to, by adding some equations. But we've got a period of substantial torque, and then the torque dies away, and the torque dies away because the speed has probably got to the point where the machine is running at constant speed, and there is a very small torque here. If we were to zoom in maybe on the, come on, don't think it likes having the video and dealing with the graphs. So it looks like about 0.4, yeah, 0.43 something Newton meters, and that's the torque that's required to just overcome the friction in steady state. I know I'm going to be in steady state because the friction is constant. The friction is proportional to the speed in this model. The load torque is 0 because I set it up as 0 just here. If I hadn't, then the load torque would end up being added to the electromagnetic torque, as well as the electromagnetic torque required to overcome the friction. And of course the net torque I expect will be dead on 0. It is. The net torque 0 because there's no extra torque. If there was net torque, speed would be changing. So that's some mechanical stuff. You can look at some other mechanical stuff as well if you want to. Here's my other mechanical stuff. Let's see if I can make this the right size. So we have some stator currents, some rotor currents, some rotor speed, and some electrical angular position of the rotor. This looks right, by the way. The bunching up of the waveform, or the increasing of the frequency, is the machine speeding up, and here we have the speed, and you can see there's a bit of torque ripple at the start. There must be torque ripple to generate this change in speed. If we went back to the torque, you can see the torque ripple there as well. And we have some rather large currents. Now, the rated current for this machine is just under 3 amps per phase. Of course, we're not loading it very much at the moment, so we don't see that. We only see somewhat less. The rated torque, I can't remember. It's probably in the write-up, maybe. If not, it will be in the machine nameplate or in the documentation of the machine manufacturer. This is a real machine, by the way. Well, obviously the simulation is only as real as the equations represent reality, but I mean the parameters I'm using are not made up. They are for a real machine, for a problem that I've got at the moment, for myself. It's not a commercial problem. If it was, we wouldn't be able to discuss it. So we have 3 phases. They're 120 degrees apart. They look very sinusoidal because I'm driving up the sine wave. If it was being driven by a power converter, you wouldn't get sine waves looking this good unless you'd really spend some money. But you don't really need them to look that good. It's just everything's nice in simulation. And we've got some rotor currents as well, and I should have thought they go very small, but not too small. 2 amps as well, and that's also, if I was to, there we go. So the rotor initially has extremely high currents, and so does the stator. So that's our, if I didn't see this sort of thing, then I'd be worried, especially the speed. You see the speed going off negative, and stopping at this speed you expect the synchronous speed, or very nearly the synchronous speed. This is not going to be quite at 1500. Oh, it's slightly over. That must mean the synchronous speed or synchronous frequency we're putting in is, well, it is 50 though. 50 times 2. Okay. Maybe there is a slight error. I should have expected that to be a little bit lower. What I might do is put some load torque on, see if it drops down properly. If it does, then I'm probably okay. We'll try that in a minute. I can look at the DQ, and the important thing with the DQ is they should be unchanging quantities, in the sense that when we're in steady state we should see no sine waves here. We should only see constant or DC, but even DC can still be changing. You can have, as long as the currents are flowing always in the same direction, it's DC, but not just DC but constant as well. Now I haven't labelled these, which is very naughty, because there's 4 things and I've no idea what they are. Alright, okay, so we've got the IS, and so we've got the stator and the rotor DQ axis currents. Well, bit of luck, the D axis current is blue for one of them, and the Q axis is yellow, and then these 2 I suspect are probably rotor currents. I'd have to go back and find out what the colour scheming is. Let's see if we can look at the properties maybe. Display, no, shan't see it there. Layout. We'll cheat, and it won't even let me do that because they're in 2 sets, aren't they? Yeah. Oh well. Bit of the model that's not quite finished to the standard it should be. You'd want to be able to see which is which, but I'm pretty sure stator D, stator Q, rotor, not sure which ones, but green clearly and blue are related to each other, and red and yellow are related to each other. Then we can look at the fluxes, and we can see we have rotor flux, stator flux. So with a bit of luck, these are D axis, these are Q axis, because D is usually the axis you would care about and Q is the axis you end up minimising. And this will be measured in Tesla, I should have thought. Bit low, but there's not much load, so it probably explains that. Righty, and then if you wanted to put it into a power converter, we can look at that as well, but I will just put some little bit load torque, maybe 2 Newton meters. Give it a run, see how we go, and we should find the currents have gone up, and probably the speed is somewhat below the synchronous speed. If not, then this video will have been a waste of time, because I'll have to see why the model's wrong. So we just let this run up. We could, if we wanted to, perhaps even watch the sine waves as they get made. Ah, great fun. Look at it go. Yes. And if we were to look at the synchronous speed, you'll see it's dropped down a bit under load, so that's okay. If it didn't do that, I'd be pretty worried. Now, as I recall earlier, the ABC reference frame stator currents are about 2 amps, and they're now somewhat more than 2 amps, although there's not a lot in it, but 2 Newton meters isn't a very large load torque, so that doesn't concern me unduly. Fluxes, I think we had about a Newton meter, a Tesla before, and we've got about a Tesla again, so I'd need to put a bit more of a load on to see that much difference. Net torque, still at 0, but the frictional torque 0.5 and the EM torque now. Before it was about 0.43 or thereabouts, so now it should be about 2.43. Yeah, nearest damn it, because we've got an extra load torque of 2 Newton meters. All that does is push this up the y-axis. Fine, so I'll take that off again. If we, I shan't save it, wanted to see it in a machine. This is quite a substantial simulation that includes the induction machine. So this is my induction machine, and I'm only feeding back a couple of things to my main simulation sort of front page, but inside it is the block we're familiar with. I think there are one or two subtle differences, like I'm pulling out a few extra things, and if I go inside it's the same model. The only difference is there's a little shunt resistor here to give the convergence a bit of a hand, but I should have thought it's a mega ohm. It is a mega ohm. So this is something I will talk about in another video. Damn you, Simulink. It's a single phase to three phase bidirectional converter with active power factor correction on the single phase side. So it's a active H bridge and a three-phase inverter. I don't propose to talk about it all now, but I'll just show you some waveforms if I have them loaded up. This takes a little bit longer to simulate, but this is my 6-switch converter, and if I was to look in it, I have 3 power poles, and if I looked in those, I've got some switches and stuff and things, and I've got some PWM and some sine waves and so forth. And if I was to fire up the scope, is there any data? No data. What a pity. Got to run it now. So this takes a little while to run. I'm going to have to think of something interesting to say. No, can't think of anything interesting to say. It's going along. We have got about 100 milliseconds so far. So if I have a look at so these aren't labelled because this simulation isn't really ready for the road yet, but it's stator currents on top in the ABC frame and stator voltages on the bottom in the ABC frame. So this is stator currents, this is stator voltages. And I don't really need to see too much more because I think we are up to speed more or less. We had a look at this little chunk here, a few waveforms. Maybe I can set it to size. We've got some reasonably nice looking sine waves. You can see the chopping, the PWM, and you can see the voltages look horrible. But if you were to take the averaging, you would see they are sine waves and they have the right phasing. This is quite common. All that's really happening here is this is the link voltage more or less, and this is the minus link voltage, and the current is smoothed by the inductance, both of the machine, and in this particular case there are filtering inductors on the output of the switching power poles, but we don't see that in the voltage. The voltage at the machine terminals can fly up to the rail and down to the minus rail as soon as the switch turns on. So it's quite common to see this sort of thing when you're actually simulating the machine and the power electronics together. But if I saw that in the lab, I'd be pretty happy, really. That's quite a nice looking sine wave. What else can I have a look at? We can look at some other things like converter and that sort of thing. If I wanted to see the torque in this particular situation, I can still zoom into this and I can still have a look at the torque. And this is our running up to speed. This is we've hit the speed that we intend to run at. Frictional torque has leveled off. We've got some torque in the system now, so I've decided to load this up, probably because I'm testing something where I want to see it loaded. And if we were to look at the speed, the computer is really working hard for this one. You can see it takes quite a long time to get up to speed. There's quite a lot of torque. It has to overcome, loading torque it has to overcome. and we've got the stator currents, rotor currents, and this electrical speed is taking a lot longer to get up to the frequency is sort of going higher as we end up with the rotor speed increasing up to the design speed, and there's quite a bit of slip now, which is why this isn't hitting synchronous speed. So that's where we're at. I will. This has nearly finished. I'll let it run. If we wanted to look at the fluxes, we could. We can see. I still haven't labelled them. Very naughty. And we could look elsewhere in the system as well. I will do this in another video more fully, but if we looked at the single phase line side parameters, we should see what we like to see. We'd like to see the current and voltage in alignment with each other. That just means the simulation's finished. Right, you'll have to stare really hard, but if the... Oh no, I've got it here in orange. That's okay. So the orange is the current, and the blue is the voltage. Pity I didn't multiply the current by some convenient factor. But anyway, this is a minimum in current, and that's a minimum in voltage, and that's a maximum in current, and that's a maximum in voltage. The voltage and current are in alignment with each other, which is good because that means power factor is unity. Of course, if we went back and looked at the voltage and currents for the machine, on the machine terms, we'll find the power factor is not unity. The machine is dominantly inductive, and we should find that the power factor changes accordingly. So we haven't really got away from anything with this setup. As far as the line side is concerned, yes, we have some unity power factor. As far as the machine is concerned, it's got the same power factor. It's always had power factor that was given by its design. It doesn't mean we can underrate this three-phase inverter. It still has to supply the current the machine needs while it's got the voltage across it that is left by what the machine doesn't have across its terminals compared with the link. So under the ideal situations, you have the smallest current across your switch, the smallest voltage across your switch, and the biggest current through your switch, and then your switch power is minimum. When the power factor is unity, that's the case. As the power factor drifts from unity, you end up with appreciable currents in your switch and appreciable voltages across your switch, and that leads to appreciable power dissipation in the switch, which is why your inverter has to be overrated when you're trying to drive a machine that doesn't have unity power factor, which is what this is all about. But we won't go through how the active PFC works now, and I won't discuss the H-bridge. It's just an example to show how you would do a simulation of power electronics and the model together, and show that the model is sufficiently well put together that you can do these sort of simulations, and you could make it even bigger if you needed to, add other parameters as well, like aerodynamics and temperature and that sort of thing. Righty, good. Email me if you've got any questions.